Now hopefully this session will be quite a bit shorter than the previous one. Now, it could happen. We're not quite there yet. We still haven't quite finished off the formal definition of the equivalent DFA, because it could be that your starting state has eta arrows. Okay? In which case you need to, with your capital E function, you need to add those states that the eta arrows point to. You need to add those states to your starting state for your DFA. Right? So instead of Q0 dashed, instead of Q0 dash just being the set Q0, we need to include not only Q0 in the set. We also need to include those states that the eta arrows point to. Okay, in the NFA. So we can do that just by doing this. Right? So we just say E of that. Because these Q0, the state in the NFA, the Q0 may have eta arrows pointing to other states, so you need to put in those other states together with your Q0. That's your starting state in NFA, but if it has eta arrows, you need to add to this state the states the eta arrows point to. Right? So your modified Q0 dash, the dash means just some property of the DFA, the equivalent DFA you're trying to find. So instead of it just being the set of Q0, it will be E of the set of Q0. And all this means is that you've just added these extra states that the eta arrows point to, because maybe your start state has eta arrows. Right? So you allow that possibility. Now, if your start state has 0 eta arrows, then this would just be the same thing as the set of Q0. Okay? So this is just an extra precaution. It allows for the possibility that your start state in your NFA may have eta arrows exiting from that state, from that start state Q0. Alright? Okay, so that's it. That's we've finished. We've actually now constructed, we've built the machine M. In other words, the DFA, that's the equivalent of the NFA that we started with. Right? So this machine M, is the DFA, and it simulates the NFA big N. Yeah? Now it works. Why does why does it work? Well, as each input symbol comes in, then the state that the DFA, N, the state that the DFA is in corresponds to the subset of states that the NFA is in. Okay? They match 1 to 1. So they're equivalent. So the DFA is simulating exactly, in a sense, the behavior of the NFA. Because at any given moment, in other words, when let's say the ith input symbol comes in, the NFA will have a set, will be in a, it'll have a subset of states, a subset of Q. There'll be various states that it's in. Because it's an NFA, right? It won't be in just one state. Usually, it'll have several. There'll be several branches processing independently in parallel. Okay, because it's an NFA. So those states at that moment, like when the ith input symbol comes in, those states, put them in a set, and that'll be the state that your DFA is in. Okay, so it obviously works, right? So yeah, that's what I'm saying here. Now, I've said this sort of thing before in the text as well. That if you're when you're doing a proof by construction, which is what this is, because we construct it, we built a DFA that is equivalent to its NFA. Now, if a construction gets really quite complex, you may need then a further proof or subproof that it actually works. You then have to prove that what you have constructed actually functions as desired. Now in this case, and for most cases in the textbook, the whole course, the construction proofs, what gets constructed, is simple enough that you don't need a proof of, how would you describe it? That it works. You don't need a proof of functioning. Like in our examples, the things that we construct are simple enough that we don't need a proof that they work. Right? But with far more complex constructions, you may need a proof that they work. And if you do need a proof, those proofs that show that some construction actually does what it's supposed to do, that it actually functions the way it's supposed to, typically those proofs will be proofs by induction. Okay, so using what, like what would correspond to your integer in proof by induction? The number of components, I suppose. And you assume that it functions well for m components, and if that's true, then it functions as desired for m+1 components, and then you show it does function for when m equals 1 components, something like that. Right? Now, in the text, there is an example of a just wondering what Sipser doesn't actually use a technical term for correctness proof, I guess. Okay. Now there is an example in text. It's part of the proof of theorem 1.54. It's on page 66 of your text if you want to follow it up. Right. So we will at least now for most cases in the whole course, the whole book. Most of these proofs by construction, the construct, the thing that gets built, is sufficiently simple that you don't need one of these correctness proofs to prove that what you construct does actually do the job that's required. Okay. All right. Okay. So right. So we've now built we now in a sense finished the theorem. We've finished theorem 1.39. We've constructed a machine M, a DFA that is equivalent to an NFA, and because it's pretty simple, we didn't need a correctness proof, meaning we didn't need a proof to show that the claim that the construct does the job required, that it actually does simulate accurately what the NFA is doing. Okay, we don't need that proof. All right. Okay. Now, given this proof, so we finished proving 1.39, our first major proof. Okay, and a big one, an important one. So now we can redefine what's meant by a regular language. Okay, we can now use this notion of an NFA and a DFA being equivalent. For any NFA, there's an equivalent DFA. we can use that now to redefine, or an alternative definition, of what a regular language is. Right? So now it's a pretty easy proof. So and it follows pretty readily and easily from theorem 139. Remember, 1.39 says that for any NFA there is an equivalent DFA. Okay? That's what that theorem says. Now that was a pretty hard proof, but now we have a fairly easy consequence, a theorem that follows from that, follows fairly easily, and such theorems tend to be called corollaries. Okay? So we have a corollary now, so label it 1.40. So this is the 40th thing that Sipser has labelled in the chapter 1. And the thing could be a definition, an example, theorem, corollary, okay, whatever. He uses what I call global ordering, which makes looking back, trying to find where things are much easier. All right. Okay. So here is the theorem statement. You know, a corollary is just a theorem, right? So here's the theorem statement, if you like, corollary statement. So a language is regular if and only if, so a two-part proof is required, okay? A language is regular if and only if some NFA recognizes it. NFA recognizes it. And this is an alternative statement to 139, right? Sort of. Now we have two mathematical statements here. Language is regular, I've labelled that P, and some NFA recognises it. That's a mathematical statement I call Q. Okay? So P is true if and only if Q is true. Right? That's the general structure of this, this statement. You can write P